Hi, David Vizard here, and you're watching PowerTech 10. Basically, this episode is the first of the rebooted PowerTech 10s, right? And I picked this one because A, it was very popular on the old PowerTech 10 channel, and B, it made statements that needed to be made, especially concerning VORTEC heads. So here's what I'm going to do here. I'm going to run improved edited version of this video now, and this is on the intake, and then the two on the exhaust to follow that. And that will be the first introduction to our new rebooted PowerTech 10. Now I have to say, I did this one several years ago before I had all my brain surgery and things like this, and it was just a tryout. It was done with a telephone, so please forgive the not so good visuals here, but hopefully the message gets over that there is so much BS about porting VORTEC heads that it needs to be set straight. With no further ado, let's get on with this VORTEC porting story. First, let's take a quick guided tour of the intake port. What you see here is a number of views taken around the valve guide as the center of the picture. This is a finished port, and it produced some really good power figures. So, with no more ado, let's get down to looking at what we need to do to get a high output intake port. You don't have to scan the internet very long to find any number of videos showing you how to port VORTEC Chevy heads. This popular head comes from the factory with plenty of performance potential already built in. But there is a downside to that. It makes it really stingy to be able to get any more power from it. And it also makes it that much easier to make mistakes in modifying it because it's already a well-developed head. What we're going to do today is to look at the modifications that really work, as well as showing why many of the modifications that you see on the internet are wrong. So to get the straight grip on this, just follow along with me. Here I've prepared a cross-section of the VORTEC cylinder head's intake port. We're looking at this because basically it's much more important to get good flow on the intake than it is on the exhaust. Why? Because it's harder to get a charge into a cylinder than it is to get it out. Here's that intake cross-section close up. I've got the valve, the intake valve, opened to about what we would expect for a typical street motor camshaft at full lift. Now, consider this. Let's look at this part of the port, right? Here's where the pinch point is, but that's on the piece that's cut off. This here, this entire section, is unobstructed. If we were to flow test that, and we will later, we would find it flowed very well. Now once the air's come past here, it's got to negotiate all of this here. And this provides quite a bit of obstruction, especially past the valve. You look how unstreamlined that is. And here's my point. When you look at those other videos, you will find the first thing they will talk about is enlarging the port here. Why? Because they don't have a flow bench. And it seems like an obvious thing to do. Well, unfortunately, it is not. Here's another view of the port. This shows where the pinch point is. This is where metal was cut away here, and I just brought this down to show this the position of the inner wall here.
What's not commonly realized is that removing the pinch point can, in some circumstances, especially for an engine build that's for the street, actually cost low speed torque and horsepower. In this shot here, we can see the pinch point better. Study this for a moment and remember that this head is actually upside down, and you will see that the pinch point is wider on the roof of the port, that's down here, than it is at the bottom, which is how it should be. Why? Because more air flows up here than it does down there. If we enlarge the pinch point there, all we will be doing is helping the port become more stagnant. In other words, the airspeed will drop, and airspeed is important. You've got to have enough to make good torque, right? So widening the port down at the bottom is almost a useless operation, so don't do it. But we'll see how that results on the flow bench in a moment. Here's one of the test sections that we're going to be working with. Something I might also explain here for those novices with cylinder head work is, when I talk about valve shrouding, what I mean is where the edge of a cylinder wall or combustion chamber is so close to the valve that air cannot come around the valve very easily, so it restricts flow. The VORTEC head, unlike many of the earlier cylinder heads, is well catered for in terms of having a valve with minimal shrouding. You see how there's plenty of clearance here. When this valve opens, such as we see here, there's a big gap there for the air to come in and swirl out past the valve. In that respect, there's very little chamber work to do, but there is some critical stuff that can be done on that, but more on that later when we get to the combustion chamber. Here we have the VORTEC cylinder head exhaust port. It's a big improvement on earlier cylinder heads from GM, but there's still some improvements that can be made. First, the seat can be made more efficient than this form here by some simple blending moves down here, and if you're going to lift a high lift, the guide itself starts to become an obstruction. So reshaping that can also pay off. As for the rest of the port, that's pretty decent shape, so we don't have a lot of work to do on that. Whilst we're doing this project, I thought I would pose the question that I'm often asked. Does a typical porting kit contain enough of what is needed to port a pair of cylinder heads? Well, we'll see here. In this shot you can see what's in the Goodson kit, and this is the one that I'm putting on test here. And I've added the two cutters that you will also need to get the job done. This here is the flow bench that we'll be testing our results on. I'll just have to remove this Ford intake manifold that I'm testing, set it up for the VORTEC heads, and we will be good to go. Here we are, ready to start flow testing. This is my trusted colleague here, Andy Wood. He's going to run the bench whilst I input the numbers that we get into the computer with this flow bench program that I wrote. This is a program that calculates all the variables and how they affect it, and from this we can tell for certain whether we've made a move the right way or wrong way for power. So let's get cracking with this flow testing. Well, here we are just getting ready to see exactly what happens when we enlarge the pinch point by just about 1/8 of an inch. We're just shy of breaking into the pushrod hole here. So with this test we'll see just what it's worth. So what do we have to show for our efforts, spending 15 minutes hacking out cast iron at the pinch point. Take a look at this graph. See that red line? That's the modified port. The blue line was the stock port. As you can see, there is almost no difference, and none of that extra flow appears on the scene until 350 thousandths lift, so it's only available for a short time. But there are some downsides to this slightly increased flow, so let's have a look at that. What you see here is the port velocity. Look at that red line. Because the port got bigger, yet no extra flow of any significance was seen, the port velocity dropped. Only a small amount, but that's a trend in the wrong direction. Two things were negative about this move. First off, because the pinch point wasn't there, air wasn't forced onto the opposite wall as well, and this effectively cut the swirl, but also it had the effect of cutting the velocity. The bottom line is that move there, although it looks like it should be a way to get extra power, actually will reduce power. So at this stage in time, we don't enlarge the pinch point, we just smooth it out and make sure.
So why was opening up the pinch point of so little use and maybe even a backward step? Well, to be honest, it's all to do with areas and local discharge coefficients. Let me explain. The air responds to the area that it can flow through plus the efficiency with which that particular area flows. In other words, a venturi flows very well. A valve does not. It's pretty obvious to look at the two and see how much they differ. Now what we're going to do here is we are going to look at the area available multiplied by the coefficient of discharge of both the valve and valve seat and the pinch point, and we're going to assess from that which one should need the work doing on it.
Here we are at the drawing board. This here is a hole equivalent to the size and efficiency of the intake valve. This is a hole that is equivalent to the size and efficiency of the pinch point. Essentially what we've done is enlarge this, which is already much bigger than this, and we haven't touched that. This here is actually, in quotes, the pinch point. This is the blockage, not here. So, from what we see here, it is evident that we need to work on the valve seat first, as the valve and the associated area is the restriction in the system, not the pinch point. That pinch point won't become a problem until we have a much more efficient and or bigger intake valve to supply. For this next move, our focus is going to be the area within about 1/4 of an inch, maybe 3/8 of an inch of the seat, just after the seat, and we are going to address this problem here. Take a look at that valve. Look at that ridge on there. That is not good for low lift flow, so we're going to do a simple move and chamfer that off with a 30-degree back cut on the valve. The tools I'm going to use for these points of rework are going to be a 3/8 olive-shaped fine cut carbide cutter, and just to finish it off, this 1-inch ball-shaped reamer. First, let's address how we're going to back cut the valve. Most of us don't have a valve seat grinder, but it can be done easily on an offhand grinder like this. Your first move here is to put the valve concerned into a drill, cordless best, and one with not too many RPM. Next, be sure to put safety goggles on. Okay, here's the job done. Note, I haven't gone in for fancy polish back here. It's not necessary. This is plenty smooth enough. But that ridge has gone. It's been radiused off into the seat. Now, important here, a 60 thousandths wide seat works about best. Any less than that and you gain nothing and sometimes lose flow. Any more than that and you definitely lose flow. The same procedure of blending that corner out needs to be done on the exhaust, but in that case we need to leave the seat a little wider, about 70-75 thousandths. Okay, a few pointers here. After you cut the throat of the port, finish it with a 1-inch ball wheel. You won't have much to take off, you can use quite a fine one. But the ball wheel is very convenient. And I'll show you how this works. Coming round here, just above the main area of the cut. And instead of cutting on the side of the wheel, you cut it about 45 degrees on the ball. This gives you a very easy method of blending the below the seat area into the seat. Now you have to be careful not to actually grind the seat. We're going to see if we can port this head without having to spend money on having the seats recut. Anyway, the other thing is you have to remember that the air comes out of the port. It doesn't come straight up, it comes out at an angle like this, right? So you'll find that there is a little metal to spare around here. So you can kind of make a venturi shape there. So this here is like a bump. And this is bigger down here. Radius into there. Right? We are trying to make the most of this valve, and that's one of the moves. Okay, at this point, let's go and see what that did on the flow bench. Here we are gearing up for test number 3. So let's see exactly what that little bit of seat work did. By the way, it's worth pointing out that you can do maybe 3 or 4 seats in the time it takes to do one port cutaway pinch point. So this is a far faster mod. Let's see what it does. What we see here is a graph that shows the difference that our seat and the first quarter, 3/8 of an inch down into the bowl rework did. As you can see here, follow the arrow. This gain here is as much as 20 CFM, and the gains start from about 100 thousandths lift. So the gains are throughout the lift curve from 100 thousandths up. These gains here are very significant because the valve goes up through those and back down. Although these gains up here, 6, 7, 8 CFM, are significant, the valve only gets to this place once. So what we've picked up here is far more relevant than just a gain right at the top end. But let's look at where we were when we had just the porting done, the pinch point done. Let's calculate that, graph it. Here, this thin line here was stock, this wide blue line here was modified. This amount of gain in airflow here was insignificant, and what happened was we lost flow down here, so we lost port velocity. So this would not have resulted in any power increase. In fact, it would probably cause power and torque to drop slightly. What you see here is a graph of the port velocity. Note that because the port size increased such a minuscule amount but the flow went up significantly, the port velocity also increased. This is a very useful increase here. The magic number for most heads, pushrod style Chevy look-alike heads, is to have the port velocity at full lift between 300 and 320 feet per second. You can see here we are nudging the 300 feet per second, so our move was not only good for more flow but also more torque. Here I have a 3/16 ball bearing welded on to a wire, and I'm going to use this to show you how shrouding affects the flow out of the valve. By the way, these tools here, just show you all that it has. They're made by a company, I can't remember it offhand while I'm doing the video, it'll come to me after, but if you Google flow balls, you'll get the company name, right? They are a very useful tool if you're going to seriously port heads. What I'm going to show here is how the flow ball can be used to detect unnecessary shrouding. First off, we're going to lift the valve just enough for the flow ball to come through, right? Now, anywhere where you can't get it past the valve now is shrouded, right? So from here to here, this valve is being shrouded by the cylinder wall, right? So we're just going to do a simple mod here and clear this away. Now, before we go any further, I want you to take note of this area here. Very important. Do not remove any metal from here, as this will produce a negative result. What happens is air coming around here wants to swirl in the opposite direction to the main body of air, which is coming out like this. And what happens is it reduces swirl and flow. So when you've finished your heads, make sure that from here to here is still a cast finish like that. You see a head that's got this polished? The guy either doesn't care or doesn't know. Before starting work on the chamber, I've put in this valve as a seat protector. What it is pretty much a 194 valve cut down so that the land, i.e. the thickness at the edge of the seat, is virtually zero. In other words, this is a sharp edge. This allows the cutter to reach right down to the seat but not actually onto it. Good idea. It will save you damaging a seat which may not need a recut. Well, here we are with the job done. I started off with this cutter, running it like that, and then for the first time so far I used an emery roll out of the Goodson kit to blend it in like this. This works very well for putting the right angle on the top of the valve seat. Now I want you to look carefully here, because there's two things to note. First, this area here is undercut so that it goes out deeper than the edge of the gasket line. But at this edge here, we must not intrude onto the gasket line. Right? What I did here, and you may just be able to see it, there it is a line I scribed that shows where the fire ring goes on the gasket. Now, as far as being able to push the valve through the seat, we have the ability to pull it through for almost the entire width here. The only place it won't come through is just here. Right, so we've unshrouded the valve in this area here only. This is something that gets missed so often, right? And it doesn't take long to do, and it's worth a few CFM. So let's go and check and see where we're at with that mod. Well, here's about the final shape for the chamber all around the intake. Right, you'll notice I still haven't touched it there. We're going to address that toward the end of this flow test session, but you'll note that we've clearanced this sufficiently to get the air past here and for it to flow smoothly over this edge. This curve here, gentle curve into the cylinder, helps generate some improved swirl, which is good for low speed torque. It's not much compared with the square boss that was there originally, but it is a gain and therefore worth doing. Let's analyze where we are so far. At this point in time, we've done the bowl, we've relieved the chamber in 2 spots, we've back cut the valve, and this is where we are now compared with the thin line was where we started from. In places we've made as much as 22 CFM gain, and this is in spots that really do affect how the engine breathes. But look, it seems no matter what we do, it shuts off up here. Maybe it's time to look at that guide boss, because now the seat and the chamber is capable of maybe flowing more than the guide boss and the port at that location will allow. We need to avoid taking any material from this area here. This is kind of a reverse test. What I've done is I've put some clay in so that we can see just how effective this area is at changing the characteristics of the airflow. Of course, in practice we can't really do this. This is a difficult job. I mean, I've never tried actually filling this in. I would think some bronze welding in there may work, but hey, by the time we get to those sort of modifications, it's a little esoteric for doing on a pair of production cast iron heads. But just as a matter of interest, I thought I would show you what this does. Now, this chamber filling is not a mod that we really want to do for a typical VORTEC headed motor, which may only have a valve lift of about a max of 550. But this is the result. As you might expect, we've lost flow in the low lift range, but from about 400, the score evens up. By the time we get to a little over 500, you can see the flow goes on increasing, only marginally. I think that's about 247 there. We've killed that dip. However, it's inconsequential for what we're doing. This happens at too high a lift for us to worry about on a typical engine. Okay, we're done with the intake now. Let's just look at the results we have. Right? Now these are real world results. You have to consider that all those tests you saw where they just ground on it and didn't show you the flow curves, you have no idea whether it's better or worse. In most cases, it was probably no better. Right, here we are at our graph drawing segment of my computer program for the flow bench. Right, we hit calculate there and then graph, and here's what we have for the flow. This thin blue line is the original one. The thick blue line is where we are now. Notice that we've made increases right from down here. Now they may not look very big on this graph, but look at this here. We've gone from 125 to almost 140 there. That's a pretty big increase in flow, and it happens in the lift range that you're going to be using on the street. At the top end we've picked up something like 10 CFM. Not big, but like I said, the VORTEC heads are good to start with, so they're pretty stingy on making gains. And of course we still have the stock size valve. Not only have we made those improvements there in flow, but here's the other aspect that's important. We've also increased the velocity. Let me show you that. Let's click there, go over to velocity, click on that, calculate, graph. Right. This is the increase in velocity we have. So we've got two factors going for us here. Not only have we increased the airflow, which is good for top end power, but we've increased the port velocity, which is good usually good for increased torque throughout the rev range. Okay, let me talk a little bit about the science of flying cylinder heads at the moment. Some of you are going to think this is a little bit beyond basic stuff here. The moves I've showed you to do are basic enough. What you're seeing here is the interpretation of them and what they're likely to do in far greater depth, and it's usually shown on porting videos on YouTube or any other channel for that matter. For those of you who want to learn to be expert cylinder head porters, and I really don't like to use the word porters, if you want to be a cylinder head development engineer for a race team or for your own business, then I thoroughly recommend that you come along and attend one of my How to Build Horsepower 3-day seminars. Just go to www.davidvizardperformanceseminars.com. All the details will be there. I hold these seminars about every 2 months, and it's a small group seminar, so we do have one-on-one contact. Well, this is the end of the line for our intake makeover. On the graph, the gains don't look super impressive unless you're used to looking at graphs of intake flow figures. But mid-range here, we've made as much as 18% difference in flow, and this is an important area. This cylinder head is now going to run as if it was equipped with a 202 valve instead of a 194. So that's a move in the right direction there. What we're going to do now is finish our flow bench work. We've looked at quite a few things with airflow that probably had not occurred to you, especially if you're a novice here. One of the things I can recommend, hell yes, I know I might be biased, is this book here, available from Amazon. This book went to virtually an immediate bestseller in this category. I think it outsells every other book on porting combined. So it'll get you to the stage where you've got a pretty good idea of what you need to do, and it also details how to build an inexpensive flow bench, about 150 bucks in a weekend's worth of a vacuum. And if you're into Chevys, this book here, well, not just Chevys, Fords, small blocks, big blocks, whatever. This here gives you how to make more horsepower that cuts across every type of engine. It's an internal combustion 4-cycle engine. This is the book you need. This book here is used in many universities at the entry level, first year automotive race students. So it's well worth getting. Both books are available from Amazon.com. Just Google David Vizard, just go to Amazon.com, put in David Vizard, and you will see a list of all the books I've written, and also reviews about it. And I think you'll find that some of my books have the highest rating on reviews on Amazon.com. I'm sure many of you are thinking that the porting procedures that I've been describing are just a little too esoteric for a beginner. That's not quite the way to look at it. What I'm doing is analyzing basic moves and showing whether they're moving in the right direction or wrong direction. There's nothing there that I've shown so far that cannot be easily absorbed and done by the home head porter. If you want to go on further in your head porting learning, teaching, career, whatever you may have as a goal, then we can accommodate that. A good starting place is my 3-day seminars on how to build horsepower. If you really want to be a professional head porter, then we're offering a 10-day porting school, which will take you right up the ladder in terms of what you can achieve and understanding how to get the best power from a and cylinder head. At this point, we've only done the intake. And if you check this out here, these are the gains that we've made. Is that the end of the trail? Certainly not. Let me show you some figures that we achieved with the port that I showed at the beginning of this video. Here are the gains we've seen so far on the intake. Observant people may spot the plots with exhaust, but though that's what we've achieved, we haven't shown yet how it's done. Anyway, is that the ultimate? No. We can go on. The port I showed at the beginning of this video is a fine example of what can be achieved by attending my VORTEC class. This is a mold of the port that went 264 CFM at 700 lift. Of course, we may not lift 700 on most street motors, but this still exceeded 260 at 550 lift. The point to note here is how, now this straight wall here is the cylinder wall side of the port, and this side here is the cylinder center. Notice how this is widened here and bulges out to accommodate where the valve guide is. This means that the area here spreads to compensate for that. Also note this curve here, and we'll get down and look at that a little later. Now let's look at the other side of the port and at a lower angle so that we can see the port bias. Study this carefully and you'll see how the port is actually leaning a couple of degrees towards the center of the cylinder. Also note how this bulges out here to slow down the air, and that this radius here will encourage flow out towards the center of the cylinder, which is out here. These are all factors which tie in. The important thing is not to overdo them and not to underdo them, and that's the trick of making these work. It's all very subtle, and that's why ultimately you need instructions like we're giving here, or you need a flow bench. Just how much better is this super port than what we've done so far with our basic porting? Remembering that we're already using the benefits of flow bench to get our basic porting stuff right, you can understand that getting any more improvement is difficult. Nonetheless, here's what we see. This is where we're at with the thin blue line at the moment, and this is where our super port is. And it's all been achieved without any loss of port velocity, and that's a key factor. We've looked at the intake in detail now, and we've achieved 264 CFM at 700 lift. That's very good. And remember, we've still only got a 1.94 valve, right? There's still more potential in this head. Given a bigger valve, we can get it up to about 280 CFM. Also, note the exhaust. This is what we're going to tackle next, and we get that up to 196 CFM. These are figures that are in the realms of good aftermarket CNC heads. So we're showing you really what works on these VORTEC heads. Now it's time to tackle the exhaust port. If you want to upgrade your porting skills, where might you go? Simple answer for that. You can either attend one of my 3-day seminars, which will give you a lot of valuable pointers on cylinder head work, plus it will also show how to build an easy, simple to build, low-cost flow bench, and a lot of other things that will get you going. Or you can take one of my 10-day porting classes, and you'll get to go from 0 to hero in about 10 days. but it's not for the meek and mild. It's pretty intense. So be prepared if you come to really work hard. There's a lot to cram in 10 days.